Thank you, everybody, for joining us for today's seminar. We have with us Dr. Mahmood Irtiza Hussain. He got his PhD from Griffith University in Queensland, Australia. He's worked with numerous renowned research teams in the field of quantum information sciences and quantum optics. Presently, he leads a project in quantum sensing at the Qatar Center for Quantum Computing. He's investigating new coherent control techniques benefiting matter wave interferometry. Thank you very much for agreeing to come here. We welcome you all, and go ahead.
Thank you very much, especially Dr. Fayyad, Professor Fayyad, for hosting this. So I won't be talking about my current project, which I'm working in Doha. Rather, I will discuss some projects which we did in the past, and give you some summary of the projects and some of our findings. So before I start, I would like to acknowledge some of my mentors and colleagues, especially who are involved in the project and the presentation, which I'm delivering and talking today. Especially Professor Arnav Vlach and Christian Felix Rules, and Professor David Dubinsky, and Eric Street, and Peter Thielwolf. So the introduction after this this introductory part of my talk, I will go straight into the quantum sensing part, where I will talk about ultraweak force sensing and ultraweak ultrafast field sensing, which I am calling transient field sensing. And at the end, I will give you some nice show you some nice pictures how the shadow of atoms look like. Hope you will find it interesting. So basically the whole talk is organized in a way that it seeks a lot of engagement from students. So things are very on the textbook level, and they're not really going into super deep physics, but of course we will touch all these aspects, which will cater the whole audience which are sitting here, seniors and all the students as well. So since this talk is mostly relying on ions, and of course we have to trap ions so that we can use them. So for trapping ions, just an introductory slide how the scales looks like in these experiments. So what we do is we use electric fields and to trap ionized atoms inside the vacuum chambers, and each ion typically represents a qubit or quantum bit, and we can manipulate these qubits using precisely timed lasers. So it's basically the whole field is heavily dependent on how you interact optical fields with atomic systems. So once we have these controls, then we can control these platforms and these tiny particles, and then we play with them. We can build quantum computers. We can do sensing. We can do many of the experiments. So this is just a picture of a very tiny quantum register. Roughly, it's 8 ions, and what you're seeing here is a laser beam focusing 2. Typically, that's how we use lasers to manipulate quantum levels. And this particular lasers, which have been shown here, is utilized for qubit flipping. So essentially, it's a clock laser. It's a very narrow luminance laser. So the inter-ion distance is roughly a few microns. It depends on trapping potential, but typically where we have this stable conditions, it's on the order of 5 micrometers. And the main thing is the laser wavelength is much tinier as compared to atomic spacing. Each this color dot is representing a single atom, a single ion. Basically, essentially, it's a fluorescence of a single ion. So this is how the scale look like. So we have the inter-ionic distance is roughly 5 microns, and the laser is shorter than this. It's very critical. If it is bigger than the inter-ion distance, then you have a lot of crosstalk. You can't build quantum registers. Then we have to think about this very carefully, which transition we need to use and which laser we're going to operate with. So all these investigations go beforehand before basically building any quantum system or hardware for a quantum system. Anyway, so the ion localization, once we trap it, so on at the motional extent where the ions we can find the ion in the space. It's roughly the dimensions on the order of 10 nanometers. Once it's captured, it's cooled down roughly within 10 nanometers. range we have is the probability of finding the ion itself. But overall, the dimension of ion, the atom is very tiny, so there are picometers. So yeah, so this is how typically we have situations in the atom.
The laser wavelength is enjoy controlled, right? So why this particular choice of size?
Yeah, it's not in our control in one sense.
You can choose, right, which laser.
Yeah. But typically, I will talk about this in the forthcoming slide. But it depends how we are defining a qubit. Either we're defining an optical qubit or the hyperfine qubit. So for the hyperfine qubits, we don't really need optical frequencies to flip the population in the qubit levels because they are microwaves in the microwave regimes. Because the hyperfine splitting is typically on the order of tens of gigahertz, which is not hundreds of terahertz as compared to the 700 nanometer light. So yeah, the short answer, it depends on the species we are dealing with, and yeah. Anyway, so this is how the basic concept of trapping. So we have typically we use some metal electrodes where we apply this G and D is the ground, the potential, and on the two electrodes we're applying some oscillating electric field. And once this happens, so these two electrodes are defining the trap ground. Okay, so basically against this reference, we are flipping the voltages. So once this is properly done, then somehow the situation looks like this. So we have, in the NV picture, so we are flipping these polarities because we have this oscillating electric field. And as a result, ions become confused. At one time, you're feeling a force in the inward direction, and the very split one after you're feeling a force in the outward direction. So I can't do this with the tens of megahertz level fast because this is very slow what I was doing. So what it happens on a very fast scale, and typically 30 to 40 megahertz, then with this frequency, somehow we can trap the ion. And yeah, so this is how it looks like in the more 3D style. At some initial time, and when you apply the RF, and then this is how the ion will feel a pseudo-potential is kind of a rotating saddle. Yeah, so, but this, I don't want to spend too much time here. It's a very introductory concept. So somehow we can define the radial confinement and the axial confinement. So as you can see on the picture, we have this axial confinement where you're applying this U0 potential. They are the static potentials, and on the other two electrodes, we're applying this yellow thing. It's the oscillating electric field, which is the dynamic potential. So the combination of this dynamic and static potential, essentially we generate a pseudo potential, so we can trap the ion somehow in 3 dimensions.
So yeah. This creates like a time-varying field with a sort of a spatially independent potential. So how do you create that spatial dependence to make a grid like one atom is here, the other is here, the other is here?
No, it's fixed in space. Mm-hmm. The electrodes are fixed. So it's fixed in space. We have to think carefully where we're going to place the metal itself. For example, if you want to trap calcium, I want to trap terbium, then we have to place a chunk of metal on a suitable position, and then we apply ablation laser, or we apply some resistive current. As I said, it produces fumes.
No, I was asking about like two ions, they have like 5 micrometer distance. So which parameter controls that distance?
This is U0. This is axial confinement.
Okay.
Because those ions you've seen before, they were aligned in this axis direction, in the axial direction, which is this U0, the z-axis. Yeah, when you change this potential, you can essentially, you can increase or decrease the interatomic space. But in the stable conditions, it typically is 5 microns. It can be 6 micron, it can be 4 micron, but yeah, typically on this order.
U0 is the intensity of the laser.
Sorry?
Is related to the intensity of the laser light?
No, it's just a static potential. U0.
As in, if I want to increase it experimentally, what do I do?
So you want to
if I want to increase it, what do I do? Experimentally.
Yeah, we'll just increase the voltage.
Okay.
The applied voltage. Yeah.
It's a control voltage.
Yeah.
And then what's V0?
This V0 is the peak potential for this oscillating field.
Okay.
This time varying field, which is
the oscillating field.
So omega is the trap, so-called the applied frequency. Okay. Yeah, but when we applied all these things, then we trap the ion. Yeah, and then we have the two oscillation frequencies of the ion, the so-called nu z and nu r. We typically call it the axial trapping frequency or the radial trapping. So radial can be in axial is typically like Professor Hoyal was saying, is in this direction. He was asking this U0 thing, so which anything aligned on the z-axis is the axial. we call them axial, and the other one, and the X and Y, we call the radial. So we have, these are the, how fast that frequencies can be. This is the basically the so-called formulas. When you check in all the numbers inside this, we can determine, okay, this is this much megahertz or this much megahertz. We have the axial frequency or the radial. Okay. All right, so yeah, but since I mentioned, don't spend too much time on trapping itself because I want to use them. So maybe any other time I can go really into details of this. But anyway, so for students, I would like to encourage them to, if you really want to understand how we trap single ionized atoms, not neutral atoms, especially for ionized atoms, this is the very key thing in the recipe. You must know how quadrupole mass spectrometer works, because ion trapping is essentially the extension of this quadrupole mass spectroscopy. So how you filter out atomic species, typically, electrochemistry people are doing this. So if I remove our things, the static potential, then it becomes a quadrupole mass filter. How these electrodes know we need to trap calcium? It's essentially a mass filter. We are trapping only that particle, but we want to trap. Indeed, it's inside ultra high vacuum environment, and everything is very nice, clean, but still, it's not an absolute vacuum. You still have some chunk of gas particles floating around. Anyway, so this is I would recommend you guys to read further. And yeah, so also especially solving math equations, and those equations will give you or tell you about how the stability regions look like. So in which region you want to create your trap, where you have from where you can learn how much voltage I need to apply, how much potential it should be. It's not like random you apply some voltage and somehow you will magically get the ion. It won't never ever work like this. You have to first solve these things, then you know, okay, which species I want to trap, how my electrode geometries look like, everything come into, and then you can essentially find those numbers, and then you start playing with those things. Okay. Yeah, they are very strapped design. This is typical Innsbruck design. People in Innsbruck, this is their, somehow their masterpiece, how they used to trap, and still they are using this kind of blade electrodes. So you can see there are a whole bunch of lasers shooting through, and the whole purpose of this to ionize the atom, and then then cool them, and then do a lot of qubit manipulations and so-called gates and so many things you need to do with it. Everything is happening with the help of lasers, with the optical fields. This is somehow the realistic picture. Indeed, it's a cartoon, but this is how it actually looks like. And also then we have on the outside of this trapping thing, we have this EMCTD or PMT, so-called in photomultiplier tubes, or EMCTD is a camera, high sensitive cameras where you can take the images, like I showed you before, the actual image of the quantum registrar of big times. Okay. Yeah. Let's go. And nowadays, people are going, the industries like IonQ and other big giants, they are trapping and not using these bulky electrodes, rather they are relying on the chips design. So we have them, like you can see here. You can see roughly more than 80 ions in a linear string of 80 ions. They are trapped on the surface. They're floating on the surface of the chip. Okay, so basically, you can see it's an 80 qubit quantum register. That's the actual image. Yeah. So it's roughly a few tens of microns on the surface of the chip. All right. So yeah, just like we were talking to, so yeah, I don't know your name. Yeah,
No problem, Zoe.
Dr. Yeah. So you were asking about this. Of course, there are different ways to manipulate those things, but right now I'm talking about is optical. How we can define the qubit in the ions. It can be optical. It can be hyperfine. Right. So it depends on the species. Either we are taking calcium, strontium, terbium, and within the terbium it could be a terbium-171, calcium-43, and it depends on what isotope we are using. So if we have depending on the isotope, either we have the hyperfine levels due to nuclear interaction and the electronic interactions, or we don't have those hyperfine levels. If we have the hyperfine levels, then we define the qubits in the ground states. It's a very nice place to define the qubit, because in theory, you have infinite lifetime. It's in the ground state. But typically, how we used to operate in Innsbruck is using optical transition. It's a bit tough. Yeah, you need very precise lasers. It's not easy to build those things, but anyway, there are two different ways, and they have different.
So what's the advantage of the top one?
The top one is you can build optical clocks.
Right.
Yeah. So it's essentially a clock.
Higher frequencies.
Yeah, exactly.
Plus, if you would use microwave, potentially you need to put an ion here and an ion there, and then very far away.
Exactly.
Because you're working with the millimeter waves.
Exactly. Then how would you avoid the crosstalk? You cannot avoid the cross tracking. Then this is on engineering point of view, it's very unrealistic because if you do like that. So again, if we want to operate these levels, then again we are using optical fields, but we are driving the Raman transitions. Essentially, we control the beat node of these two red arrows. They're counter propagating, and we control the beat node of those frequencies. So we drive the Raman transitions. Essentially, we just sniff the excited state and go back to the other state from ground to but within the ground states. All right, yeah, then let's keep going. So this is how there's a very, very simple picture of an ion. In reality, ions or atoms are very complicated. But what you're seeing here, I'm just showing those levels which are most interested. So yeah, but how we image the ions and how do we know it's in the excited state, in the ground state. So here's the recipe. So this is the 3 level for the calcium 40. And we are dealing with 2 different transitions. The one transition is so-called dipole transition, you can see on the blue line. And the red one is the quadrupole transition. It's a clock transition. This is here we are defining the qubit. Okay. So now, and this is our qubit. That is our qubit state up and qubit state down. I don't know where my ion is, what's the state of my qubit, unless I do this operation. Okay, when I shine the laser on the blue thing, if somehow this fluorescence happens, because this is a dipole transition, look at the lifetime, it's 7 nanoseconds. It's very fast. It decays very quickly. And look at that lazy guy, 1 second. This is a C difference. So which means if I apply a laser on this line, it very quickly decays and produces a lot of photons. I can use them to image the ion. And from there I can learn in which state my qubit is. Is in the ground state or in the excited state. If it produces fluorescence, then it means I'm in the ground state. If my qubit is in the excited state, if I apply this field, then nothing is going to happen. So in the up state, there is no fluorescence. It remains the dark. So from there we begin to figure out, okay, infer it's in the state up or state down. Okay. Yeah, the thing is, I need to go way ahead. I think I'm very slow, but I think it's okay. So one step, what's next? Still ions are jiggling in this potential thing. I'm talking for a while. We can't image them right now. So roughly you can estimate their velocity is roughly 0.5 kilometer per second, roughly. Just a rough estimate. So what's the solution if you want to really use them? You need to further extract the kinetic energies from those particles. Okay, and for that what we do is we do some cooling. And for cooling, we need a little bit more complicated situation, right? So what we do is we apply these 2 laser fields, the 397 and 866. Please forget all other things for now. So what 397 is doing is exactly the same what I showed you before, the blue transition, right? And this red one is just the leakage, the population leakage, where there is some finite probability. If you excite from S half to P half state, the some population leaks into D3 half state. It's a dark state. If this happens, you can't see the ion. So we need to replenish this process. Then we apply another laser, and then this cycle completes. So for the cooling cycle. So we apply this cooling laser, and then we call it typically repumping laser, repumpers. Okay. So which means after when this Doppler cooling happens, I will tell you in the next slide how this very simple process happens. Our velocity shrinks from 0.5 kilometer, roughly 0.5 meter, which is not bad. But there are many other cooling techniques. If you have chain of ion, if you have if you have a lattice of ion or something like that, then the cooling techniques are very challenging. They're not like just use this and you will be done. No. This is a very minutes for cooling. A very preliminary process, Doppler cooling. And those processes are given here. For example, resolved cyclic cooling, electromagnetically induced transparency cooling, which we create a coherent population trapping. And also this PGC, polarization gradient cooling, so-called Sisyphus cooling as well. I'm not talking about these techniques today, but I only focus on Doppler cooling because a little bit touch this resolved cyclic cooling, but in the forthcoming slides. So how Doppler cooling works? As I mentioned, I really need the attention for students, so that's I included very simple diagrams. So you guys have already heard, or pretty sure you have understood this thing in your high school, that there's some Doppler effect, but you mostly have studied those things, sound, right? If the thing is going away like ambulance or whatever, and the pitch is increasing or decreasing, same thing happens but in lasers. with reference to the ion, with reference to the movement of the ion. Okay, so this is what we have learned already. So if I make this symbol as an atom and the person who was standing at photons, now if atom is moving towards that side, that will feel a high frequency, and if it is the other one will be a lower frequency. So what if I manipulate the frequency such that I can overcome this movement? I'm undoing this effect beforehand. Then I can use it actually. Then I can use it, then I can create this condition. Then I can absorb this coherent process, I can trigger this coherent process while it is moving. I can absorb this thing, and when it emits, it's a spontaneous emission. And the spontaneous emission is in coherent process. It can emit in any direction. All right. But when this emission and re-emission emission happens, then each time it will feel a momentum recoil due to conservation of momentum. So for one photon is just 1 h bar k. K is the wave number of the light. Okay, so this is how, if you scan the frequency on the dipole transition, which I showed with the blue one, that's how the line profile looks like. This gamma is the transition line width, and we typically operates at the center where the slope is maximum, so that we have the maximum leverage, because we don't know what's happening inside the ion. We can't see the ion. We have to just guess, oh, okay, it might be this velocity. Let's try to operate in this situation where we have the maximum chances to interrogate those transitions. So that's why we typically operate them on this when the slope is maximum. So the chances high, there is a probability the ion will come in one direction, and it will absorb the particular frequency. And then we intentionally red-detune the laser from the natural resonance frequency of the transition. Okay. So once this happens, then if ion is moving towards the laser, it feels a friction force. It absorbs, and when it releases, it feels this spontaneous emission scattering also. So which is so-called heating. But what we need to do is we need to create a condition that we want to overcome this coherent process over incoherent process. If this happens, then we can create cooling. We are cooling, we are heating, of course, but we have to overcome heating. And fortunately, spontaneous emission is incoherent. It can happen in any direction. So somehow it averages out. But the coherent process is happening mostly in one direction, any random direction. It depends on the laser propagation, so many things. Yeah, but if you plug all these basic ion trap numbers, so the rho E is the excitation probability, and then trap we have this condition, and the radiation pressure I told you, because in absorbing a photon, there's a radiation pressure. We have to equate those things in the trap. They are balanced. We have those stable conditions. If we equate those things together, then we can calculate rho EE, and we know what numbers we are using, and omega is your Rabi frequency, and this gamma is, I told you, the transition line with, delta is the tuning, nu is the velocity, and again this k is the wave number, everything. If you put all these numbers over there, you get roughly x equal 10 nanometers, which I was talking the spatial extent, where you can find the ion. It's roughly 10 nanometers. Okay. So roughly is indeed a sub-wavelength localization. Straight away after Doppler cooling. So in ion traps, we can get this. So in steady state, the important thing is, if you use this Boltzmann constant as temperature, is a very basic relationship, you can get the 0.5 millikelvin of the temperature, which means depending on how fast you cool the excited state lifetime, because this gamma is directly connected with the excited state lifetime, you can get the very low temperature. But typically, especially in this situation, we have 0.5 millikelvin, which means this is the bound. We can't get further below than this with this process. We cannot. We are bound by the lifetime of the transition. We can't change it. Okay, so if trap frequency is less than gamma, then this condition fulfills. This gamma is the transition line width, and trap frequency, I told you the frequency with which I was oscillating inside the trap, the radial frequencies and the axial frequencies. Okay, and now you can ask me, okay, this is good. But typically in ion traps, we talk about sidebands or sideband cooling and these kind of things. So where does the sidebands come from? Again, it depends on the reference. So as key, if you have the laboratory rest frame, you will see if you have a laser with some certain frequency omega L is hitting the ion. So this is how it will feel. The ion will feel if you are in the rest frame of the respective laboratory. But if with respect to iron, how iron feels is like that. Because it's moving. So which means it will have some distinct, some motion degrees of freedom adjacent to this transition line with the bigger one, the peak. And those are separated by those trap frequencies at which ion is oscillating inside the trap. We call it trap frequency. And typically this new. And typically this trap frequency is on the order of 1 megahertz. Typically it's on 1 megahertz. So which means if I have this optical transition, and if I have some narrow line with laser, and if I can change its frequency by 1 megahertz, I can actually talk to that thing, those mid-level blue things, the peaks separated by a new frequency. I can actually talk to them. Those are so-called sidebands. And it's possible to absorption to be happen on those sidebands as well. So while doing spectroscopy, you have to be very careful with which transition you are talking with. Maybe you're talking with sideband instead of the actual frequency. Okay, so let's not spend too much time on this. Just a very quick concept here for the resolved and unresolved sidebands. So this is a very basic, I would say, criterion. This gamma is a transition line width, nu is a trap frequency, it must be greater, which means you are in the Doppler regime. So no, I want to really cool it down to below a Doppler regime, I want a motional ground state. Yeah, you can do that, but you need to go with gamma less than nu. Which means you have to find a transition, which is very narrow, and then talk to it, if you can. Okay, and this is what typically we do for further cooling the ions. We need those lasers. We want to operate them in this gamma less than nu. Nu is the trap frequency. So now in the trap we have this the ions are trapped. They're oscillating, and which means we are coupling the motional degrees of freedom with the internal levels of the ions. They're inherently coupled. So like you see, we can initialize the resistor in two different in the motional modes. So here we have this stretch mode and the center of mass mode. But when you increase the number of ions, there are many other modes, like rocking mode or zigzag mode and this mode and that mode. So we have to interrogate all those modes effectively. Maybe we need to cool them down depending on the need of the experiment. But this is how it typically the situation look like in ion traps. So I was mentioning, if you really want to go down to very low temperatures, then you need to talk to those transitions. And I told you already in the last slide that they're inherently coupled, the motional state and the internal levels, they're coupled now. And if I manipulate those levels with a very precisely frequency tuned lasers, and I can effectively change those population from spin down to spin up without changing the motional mode, without adding a phonon. Okay. Because right now it's in the so-called, it's called the recoil limit. We're below the recoil limit. I told you, if one photon absorbs, then we feel a momentum. It either it's releasing or absorbing, it will feel a momentum, right? But at these temperatures, we went below the recoil limit, so-called the lambda regime. This effect is much smaller between very cold temperatures. And now if I scan that narrow line of frequency, I can actually see the carrier transition, and I can see the red sideband motional mode. I can see the blue sideband motion. So if I keep my laser on blue sideband like this one, what is gonna happen? I will heat the system. On each time I will add one phonon, because it's a Fock state. It's a combination of Fock state of the internal levels, right? But if I operate a system on the red sideband, I will cool it down. But when it reaches to a zero state, nothing is going to happen, because beyond this there is no level. We're in the motional ground state. But effectively, you can write them in this simple Hamiltonians, the James Cumming and anti-Hamiltonians. You represent this process in this form. Okay, now to the actual thing. Sorry, this is just introduction. So how we detect the ultra-weak and transient field sensing? Okay, are you ready? Good. Then this is the horrible picture. I don't want to explain this. But what's happening here is this. We developed this thing for some other experiment, but with the other experiment comes with some other problems. And those other problems give us some other more opportunities. And then we thought, okay, how we can detect those transient fields with atomic coherence. Here's what's happening. So that black box is producing an ultraviolet frequency comb. It's seen at 3 nanometers. And each pulse, frequency comb is a pulse laser. Right? Frequency comb is a pulse laser. It's a laser. Right? So the pulse speed is 200 picoseconds, which means after every 200 picosecond pulse arrives. Repetition rate is 5 gigahertz, in other words. So pulse duration was 1 or 2 picoseconds, roughly a few picoseconds. And the requirement of some other experiment, I won't explain it, was pick one pulse out of 5 billion pulses. But when I'm saying we have the repetition rate of 5 gigahertz, it means we are producing 5 billion pulses per second. But for our experiment, we need only one pulse every millisecond, which means out of 5 billion pulses, we are selecting only 1,000 pulses every second. Okay, which means we have really shut down the whole system. And now if we characterize this optical field, and we use the conventional pulse characterization techniques like frog and so many other things, it doesn't work. We don't know what we are shooting onto the ion. So we thought, okay, let's use the atomic coherence itself, that 7 to 9 thing, the clock laser, or sorry, the qubit itself, to infer the information, how wide this field is, to sense this thing. So that's the whole rough summary of this experiment. If there's any question on this, then I can proceed further. Huh? Okay, then you might think I have suddenly switched to life sciences, but this is not right. Still, we are in physics. But there are different techniques to characterize complex electric fields or complex lasers. So, but this is these were not really working. They're all their acronyms. This is what this is actual acronym. I mean, it's not a it's actual acronym. So they were, maybe somebody invented frog, another guy invented spiders, and they keep doing a tadpole and sea mudpole. Then still it's coming up like this. Anyway, but they were not working. Long story short, okay, we thought, okay, what if we have a situation like this, and the typical, frog or typical autocorrelators, where we have the pulse, for example, the electric field. This is the pulse we want to characterize. And what we typically do is we use a beam splitter and we split a single pulse into two. Then we overlap onto a nonlinear medium on a crystal. And then we generate another harmonic frequency or some try some nonlinear process to see what's going on in the n omega naught or some higher order thing or lower order thing, depending how they're driving. So what we thought, okay, well, let's replace this thing with data. Okay, and use the atomic coherence to characterize this thing. So we just replace that guy with data. Okay, and then what happens is this following. This is the protocol. This is the sensing protocol. So firstly, we are overlapping pulses, and we are overlapping those very weak fields onto the ion. And then we try to infer how large the width of that field is. Okay, so this is the sensing protocol. So first we prepare the ion in the ground state, and then we create a superposition of the qubit levels. So which means we have half of the population in the excited state and half of the population in the ground state. Or half of the electron is in the D5 of half is S half. Okay, and then we drive this process, which I'm calling ultra fast wrap. Forget about it. It's just think as a transient field. We shoot the transient field. That 393 was our transient field. Then what happens? We take half of the population from S half to P3 half. We drive this process, and then we repeat again this with the second part. We measure the relative phase between the qubit levels.
So, do you mean that did you create the plus state, which is the coherent superposition of ground and excited state, or the statistical mixture of 50% ground and 50% excited states?
Yeah, it's basically just a linear superposition.
Okay, so then we don't really know if before measurement if 50% are up and 50% down.
Yeah, we don't know.
Okay.
It's just a superposition. So, but it's there.
Because plus state is very common in sensing initial state.
Yeah, but we can verify these things with amplitude interval. But anyway, then we drive this process, and then finally you measure the relative phase between S half and D phi state. So this is the sensing protocol, and then we repeat the whole process with different time delays of the pulses. Okay, and this is what happens. So this is what happens. So we made the relative phase in the Kubert state after kicks. When I'm saying kick, and that transient field is imparting some momentum, right? So don't confuse with the word kick. But essentially what happens is we prepare our so-called quantum state in the motional ground state. And when this is displaced, so the ground state is so-called coherent states, right? Displaced vacuum states. The quantum optics people know better. So that's why we have gone like this. Initially we prepared somewhere here, then we apply those transient pulse that give some kick, and then this goes somewhere here. But since the pulses are coming in two directions, either that kick can coherently add up, or it can destructively doesn't add up, right? There are two situations. So if any situation happens, and essentially we're embedding those processes inside 2 pi by 2 pulses. They're just a basic Ramsey interferometer, right? So we prepare our qubit in a superposition, pi by 2. Then you apply those transient fields, and then you measure again what's the relative phase between those two qubits with another pi by 2 pulse. So when we measure everything, when we are sending the pulses only from front side, or we have not a bad situation. The phase was close to 1, the remaining phase. Back side also okay. When we send the pulses like this, front and back, it's very poor. It's very bad. It's 0.081, which means we are really canceling all the things. Something is bad is going on. So, but for the reference, when there's no pulse, that's our reference 0.98, get close to 1, right? So now we need to figure out what happens when we are sending the pulses from front and the back. So to figure out this thing, we apply this, we thought to rephase let's do this experiment, the so-called spin echo, rephasing the coherence. So essentially what we did is we add another pi pulse between those pi by 2 pulses. And our transient pulses, these colorful there's the rainbow thing. And when this thing happens, then we actually see we can actually produce entanglement and disentanglement and disentanglement between the spin and the motion states. But either we are imparting a momentum or we are not imparting a momentum. So when we are in midway situation, essentially those internal states are entangled with the motional state. Essentially the single ion itself entangled with itself. So the internal levels of the ion is entangled with its own motion. This is what's happening here. Okay. But now at least from this we know for a certain situation, for a certain time situation, we have an opportunity where we have the maximum phase, leftover phase. And if we operate the system in those situations, like here, or here, then we can enjoy that remaining phase from the system, right? So, but this is just the how we drive this thing with this a displacement operator we apply on the coherent state, and then we get this formalism, and we fit the data with this thing, and that give us the mean motional phonon number of 20. And typically this is okay, and that's how we also thought about it. Okay, but the main thing is we know at what times we have the maximum coherence. Now, if I operate the system on that time when we have the maximum coherence, actually I should use this. Yeah, so when you have the maximum coherence, and then we start displacing those pulses. So basically, the pulses were not overlap, and then they overlap, and then they're not overlap again. It's just like that, right? When this happens, then we have the maximum coherence. The start somewhere here. This is how your Ramsey fringe look like, the maximum contrast. But as soon as they start overlapping, there is destructive interference, and we lost the amplitude. The amplitude is washed out, the contrast is washed out, and then again we get it back. We got some signal, but we don't know how to get that information that okay, this field is this much big, or what's the width of that pulse, and this kind of situation is still an open question. So initially we thought, okay, let's try to apply just this fitting thing and then try to get the sigma value, and that will give you this inverted Gaussian thing. This is your pulse width, but we were totally wrong. That's not the case. Yeah, the situation was very much more complicated because those fields, those colorful pulses, they are essentially shaped pulses. I have not mentioned this before. And then the chirp means they are not bandwidth limited pulses. Okay, they are chirped. There is some dispersion inside them. So when those chirp pulses interfere, the atom is somehow standing in a situation which is chirped. And that thing, it produces some shaking effect on the ion. It's not really a momentum transfer. It's a weird shaking effect. And we found that this thing is heavily dependent on this complex picture. But if we come up with this Hamiltonian, and if we use this Hamiltonian and do some theory, then we can come up with the fit, this particular fit thing, the data which is fitted now. And that gives us the estimation of about 3.71 picosecond. And we were expecting that we have added a GDD, this guy, group delay dispersion of roughly 2 picoseconds squared, for the second order change in the phase up to the frequency. So, and that gives us roughly similar estimates. Okay. So yeah, so this is, I don't want to go into much details for now because I think I already consumed a lot of time on the introduction. So let's go to the other part of the experiment, which is the more interesting. And that is the ultraweak force sensing. So this is actually like that. We have read this thing in your high school, right? Mass attached to spring, applier force, and there is some restoring force and some this kind of stuff. And you can write those things. But here what we're doing is we're replacing that big mass with a single atom. And you have heard about this thing, this restoring constant and everything, right? So we are doing the same thing, but what we have here is we have 3D secular frequencies. And those restoring constants are essentially replaced by those trapping frequencies in the trap, which I mentioned in the start, with which ion has to oscillate inside the trap. Right? It happens in the x-axis, it can happen in the y-axis, it happens in the z-axis. So we have 3 axes of secular frequencies, so-called trap frequencies. Okay, now if you exploit these 3 trapping frequencies, we know the ion has a very tiny mass, it's a single atom. And if you can somehow image the position of the ion with a very high probability, then we can somehow back engineer those data and convert them into a force. And that force is very tiny, provided you can locate the ion. It's ion localization, no atom localization thing. And we have used high resolution imaging for this. All right. So I already mentioned, just a reminder that the ion is in the trap and there is some trapping frequency associated with this, and those trapping frequencies is analogous to that spring mass system. But yeah, ion is bounded inside the trap, right? It is also what is bounded. All right, and this is how the apparatus looks like. What we have is we have the trap ion, and these are just the trapping electrodes. And this coil-shaped thing you're looking here is just a very sophisticated optics to collect the fluorescence from the ion, right? To collect the fluorescence of the ion, and this is your image plane, some clever camera or whatever, where we can take the image of the ion. But if the ion is not displaced, let's suppose this is the red is the initial position, so here you will see the image. But due to some external perturbation or some force or some electric field, whatever hit the ion, and somehow it changes movement, and then the image is displaced on the image plane. Okay, and if we somehow quantify this distance from here to here, if you know how much displacement happens, then somehow we can back engineer the thing to quantify that force, because we know the spring constants, we know the trap frequencies. Okay, and to do this, which means the magic thing is this coil thing. Very important, very critical, the workhorse on this experiment. And that workhorse is just a very basic definition that is known as phase Fresnel optics, phase Fresnel lens. So unlike those conventional bulk optics where you have this kind of bulgy thing to produce, this focusing or defocusing effects, which is based on this principle, on the refractive principle. Here we are based on diffractive principle, because when you create this kind of situation, and basically, you remove all the unwanted part of the mirror or the material, such that you have the constructive interference at the focus. It creates a so-called hologram, and we call it the phase Fresnel lens at the focus. Okay, that's hologram of an ideal lens. But the thing is, this is very, very thin. This is very thin, which means we can really place it very close to the atom, right? It has a big belly, this guy, this refractive guy. And it's a child particle. Just think like this, a child particle, and these materials are made up of silica, fused silica or whatever, right? And they can also get charged. And you are dealing with a single atom, and if you get a charge on the surface of this, then you cannot image that ion, never. You have to be very careful, which means that's why this thing, this thin thing, the thin lens, this phase Fresnel lens on the right side has advantage, right? If you use them properly, we can really place it close to the ion, and somehow we can increase the numerical aperture, which means how much light we can get from the ion. Because the more photons you can get from the ion, you can get better sensing. Because they scale with the square root n, with the short noise limit and the Heisenberg limit and all those things. More photons, better scaling, right? So it really helps us. And for our PFL, our phase Fresnel lens is giving us m squared. M squared is just the beam quality number. How nice is your laser beam? It's pretty close to 1. Pretty close to 1. Which means we can get, if we pass a light through that lens, we can focus it down to roughly 350 nanometers. It's very tiny. Those who work with lasers, you guys know very well. So that is a good thing. And this is how these microfabricated lens look like. This is the actual semi-image of that piece of optics. And this is how your 3D force sensing data look like. So you can see we intentionally applied some probe voltage onto the electrodes. And we have those trap frequencies on x-axis, y-axis, and z-axis, which I'm calling the secular frequency and the trap frequency. We well determined those things as nicely as possible. And we can then, basically extrapolate all those things into a force, which is in the zeptonewtons. So we can see in the x-axis, in the y-axis, in the z-axis, you can ask me why that force is big number is so big, is it tiny, is it okay? It all depends how well your ion is confined, because on the axial direction, it is directly facing those electrodes. There's a very tight confinement there. But in the radial direction, the confinement is a bit loose. That's why we have different situations here, right? Those numbers. Yeah, but this is a very, very basic and a rough idea. Beside many other technical details, but this is just a rough idea. And the error bars are less than the size of those data points itself. So that's why you can't really see them. At least you can see them here, but not there. Okay, but this is how we measure the force sensitivity. That's roughly 350 zeptonewton per root hertz. Now you can ask me, what is this root hertz? What is this? So the students might be wondering, you're measuring a force, what is the hertz doing there? Maybe you guys know already. Do I need to explain it? Should I go further, or you want to?
It's better if you explain it.
Yeah. Okay, so basically, when you're building a sensor, essentially the sensor is, for example, this is also quantum sensor, right? It's a single ion atom. So it is exposed to the field for some time. Okay, it's very sensitive. Sensitivity brings some other problems as well. It's not only detecting the right field you want to detect, but also some noise as well. So what we do is, when we take those things, we take the Fourier transform of the data, and then we bring those data points in 1 hertz, or for 1 second, we see how much noise we have in each bin. This is a standard way of doing that. And then you take the RMS value, root mean square value. When you do this, then this is the most standard way of defining those sensitivity parameters. So for example, you have magnetic field sensor, you weigh in a nanotesla or picotesla, but you have some root hertz as well there. Same goes for here. We're detecting the zeptonewton forces, but there is again that root hertz number. It's a very standard way of basically defining the sensitivity for the sensors. You can also change. This is not like it's not coming from the Bible. You can change this. You can change the bandwidth. It will be different. It can be 10 hertz. It can be 0.1 hertz. But the standard way of dealing, when you really comparing apple with apples, is typically on the hertz level. Okay. So then how we verify that force? We are detecting a very tiny scale forces, zeptonewton, blah, blah, blah. How we verify that thing? So this is the answer. I told you before that we are dealing with those quadrupole transitions, and those transitions have very short lifetime, which means what? It will decay very quickly. But if you keep shining the laser on that transition, it will produce a lot of photons. The lifetime was roughly 7 nanoseconds, which means we can produce roughly 1 to 2 million photons per second. So depending on our collection efficiency, still we can get some decent number of photons. Decent number means typically in ion trapping experiments, we can collect, I would say few tens of kilohertz per second. Those fluorescence rate. Okay. So now if we know the exact that scattering rate, then we can determine that gamma, the scattering rate from here. And from there we can infer the force. Here's a very simple thing. You need to determine the scattering rate. If you determine this, it is very simple here. But you can see here on this this picture inside the thing, this plot. So you see, if we increase the laser power, the counts are going high. But at some point, the transition will saturate. It won't going to respond the way it is responding initially. This is called a saturation parameter, and that S is employed here. That S is here, this S in the formula S. That is saturation parameter. So which means we can determine all those numbers nicely. We know what's going on. We know how many photons are we producing and what's the lifetime of that thing. It's all naturally fixed. From there, we can educate ourselves. Okay, how many photons I should expect at this time? Okay, it's an incoherent process, but still, how much force I will expect at this time? If that force really resonates with the movement of the ion, because we are calibrating that force against the displacement, right? If that two things matches, then we can say, okay, we have effective net force of 95 zeptonewton. Okay. So this is the one of the experiments, beside other experiments, how we verify that force, and that's how it looks like. The displacement, it goes on and on as you increase those scattering rates, right? But this ion is like a tiny light bulb. Like a tiny light bulb, it's emitting photons everywhere, just like this street light or light bulb. But depending on the photon it's emitting again, it depends on the lifetime. The power is only 30 picowatt. If you ask, okay, I need 30 picowatt bulb, just trap an ion. The fluorescence from that ion is roughly on the order of gives you this much power. Right, yeah. So this is the workhorse I told you before. It was just a wavelength scale imaging and the near diffraction limited imaging. So this is the image of that single line. One of the image of the experiment of the single line is show you here. So we fit the two-dimensional Gaussian fit on the ion image. And if you take the sigma value of these two Gaussian distributions, you can see this is 378 nanometers and this one is 393 nanometers. Now here's the thing, why I'm saying this wavelength scale imaging, how do I know? Because the laser or the transition I'm interrogating is ultraviolet. Wavelength is roughly 370 nanometers. So which means it really matches with the wavelength I'm using and the width of this distribution. Because our image is roughly on the same order. Okay, so that's why it's close to wavelength scale. It's not absolutely diffraction limited, but nearly diffraction limited. All right, so yeah, but if you want to really scale this thing, this much force, if you ask, okay, how much this force is, this zeptonewton, it's roughly a gravitational pull between two persons who are sitting, one is in Karachi, another, sorry, the spelling of Karachi is not right. The one is in Karachi, the other was in Lahore. So this is how you can say, oh, this zeptonewton is roughly very tiny force. But you can detect those forces with this technique. Okay. There are some quantum limits. So the uncertainty associated with the force and uncertainty in detecting the displacements. Again, as I mentioned, the fundamental limit is how well you position the ion, how well you detect the ion position because of the displacement where the ion it is right now. That will give you the information. So it all depends on the ion position, and that is heavily dependent on the photon collection efficiency. So that is the reason why we spend so much time on building those optics, those physical optics. Because otherwise you can't really collect a lot of photons, and you don't have high numerical aperture optics, then you can't really do those nice experiments. You can do, but not that sensitive. Okay, but roughly still we're still 24 times and 21 times within the quantum limits for the x and the z direction. X is your axial direction, z is the in the focus direction, one of the radial directions of the track, which I mentioned in earlier slides. So if you say, okay, how you can further increase this thing? Keep going. Why you stop at zeptonewton? Why you go for zeptonewton or further or less? We can, but you need to find some other thing. For example, as you can see on the sensitivities, it depends on the lambda, the transition you are dealing with. And I mentioned we are already dealing with 370 nanometers. It's ultraviolet, kind of ultraviolet, yes. So, and that was the electric dipole transition. So also it's a very, very strong transition. And I'm saying strong transition, what does it mean? It's respond very quickly. The lifetime is very short, right? If we somehow find a transition atom which is even shorter, with a shorter wavelength, then you can get better sensitivities here. And also if you ramp up the collection efficiency, because in our system, the collection efficiency was only, if I'm not wrong, really is a couple of percent. And I'm saying, oh, we're producing 2 million photons per second, but we only successfully collected on the camera a couple of percent. Maybe still less. I'm exaggerating. Yeah. So there's a lot of room to improve. Hunting new transitions from UV, deep UV, much deep UV means further less wavelengths. We can increase them. Now, this is I intentionally put this on the title because we use the same apparatus to capture the shadow of an atom. I was not involved in the experiment, by the way. When I joined the group, the experiment was done. But since it's such a nice experiment, and we use the same apparatus for doing those sensing experiments, that I really wanted to show you these guys. This. So this how, especially for students, so that keep them tight on the seat. They can actually, wanted to tell them and show them this kind of pictures. This is the actual picture of shadow, which I will show you in a moment. It was captured in Kilpinsky group at Griffin University, and the whole idea is following. They use the same phase Fresnel lens, which we are using for our imaging and for detecting tiny displacements. That's okay. But they use the same situation, and what they found was, if they throw the light from on the ion, and somehow when the light passes through an object, it diffracts somehow, it interferes. This kind of thing happens, right? It creates some interference, right? So they observed a similar thing. They choose wisely which wavelength they want to use. Of course, they can't just randomly choose any wavelength, because ion has to absorb some particular wavelength, right? Which means they have to think first, okay, which transition I'm going to talk about. But when they do all those things, they use this optics, and the focus, they actually see those diffraction patterns. So it looks like this. This is the actual picture. So the center, you can see the actual shadow. You can see a shadow, yes. Because light cannot pass through me, and you can see the shadow on the floor or whatever. Same thing is happening on the image plane of the ion, but once the light passes through the ion, on the image plane, you will see this thing. Okay. So yeah, so which means with the same apparatus, many other experiments can be constructed. Any questions with this so far?
So in this image, is this diffraction pattern of something else? Because it's not concentric with the atom.
No, it's just what you're seeing is some intensity response of the pixels of the EMCDT camera.
Okay.
Yeah, because this is the image of the camera. So how much single pixel is, of course, is photon sensitive. So how many photons it's exposed to. So depending on the wavefront of the light and so many things, so those things will vary. But actually, it gives you the same impression that actually you are seeing somehow those diffracted patterns onto the image plane. But the main thing is at the center where the ion should be, it's really dark. It's really dark. So the actual title of the paper is Absorption Imaging of an Atom, but not the shadow. Just keep it a bit interesting. Yeah, but National Geographic actually, posts like this, the shadow of an atom, all this. Yeah, I'm not going further. This slide, if you have more questions, please feel free, and I'm happy to answer. Yeah, from this side or from the other one. Yeah, just feel free. Any question, please.
Excellent.
All right, so let's thank the speaker. And we can bring in questions. We do have some questions that the online audience asked.
Yeah, please.
It's possible that I missed some stuff, but it seems to me that some people are just asking questions with which they're interested in. So somebody, for example, has asked, what is the meaning of valley polarization and asymmetric distribution? I don't know. Somebody asked this question. Maybe you want to clarify this question a bit? Does this mean anything to you? Valley polarization and asymmetric distribution? You can just ignore it, I guess. Mudassir, could you just, if you can clarify the context in which you want
Which
to know.
slide or so that I can make.
Yeah, I really don't think it's related to a slide.
Okay.
But that's fine. Then we have another question from somebody who's asking, why are we using lasers to cool ions?
Yeah, it's just very simple. Okay, so first we can't touch the ion with our hands. I mean, we of course we are touching all the time, but we want to really cool them, or really want to use them for an application on a quantum scale. Then the only one way to interrogate them, especially because when they're in the vacuum chambers, you can't put any physical thing inside. The only thing that can propagate through the vacuum is the light. That's a very, very, very brief answer. Beside many other distinctions. So the light is the only tool we have. So the laser is the only tool we have to really interrogate with the atoms, because and the other thing is, atoms are basically a bunch of different energy level transitions, right? There is structure. And if you want to talk with those structures, basically those energy differences, and most of the time those energy differences lies in the optical range. Most of the times, as we were talking in the two different parts, two different situations of the qubit schemes, it could be hyperfine, it could be optical. The same goes for the cooling and these kind of things, because, like, for example, those dipole transitions and the cooling transition, where I'm saying the cycle is very fast and this and that. All these transitions are, by nature, they are in ultraviolet wavelengths. So we don't make them. Nature gives us like this, and we only use them. So that's why somehow we are bound to use those light fields, our so-called lasers, to interrogate those transitions.
Right. More questions from people here? Go ahead.
First of all, it was very nice talk. I want to know why you are using picosecond pulses. Why not?
Yeah, there is no problem. Yeah. So that thing actually, this guy, right?
Yeah.
Like I mentioned, I didn't explain this whole thing, because this whole setup was developed in roughly 7-8 years. So the whole purpose of this experiment was different, right? I'm not explaining those things right now. It takes a lot of time. But the problem was at the end. Maybe I can show you here, like this way. So this is the whole frequency comb. This is the whole frequency comb setup, which is somehow industry was not happy to give us, because it's technically complicated. So we built the source by our own in the lab. And at this point, we are sending those optical pulses to an ion trap. So the idea was to build fast quantum logic gates. That was the actual experiment, right? But before we send them onto the ion trap, we have to characterize what we are sending onto the ions. Right? So for characterization, there was, like I mentioned, for characterization of this field, especially when the situation is like that, you are picking a one pulse out of 5 billion pulses. Your nonlinear devices struggles. You can't operate. So they can't really operate. So you need some power to feed them so that they can give you some response, some nonlinear response. And nonlinear response is mostly power hungry. It's nonlinear. So, but we can't operate these devices. That's why I just give you some There are so many devices there available, or in the literature and the industry sports, but they all failed. They were not supporting us, especially in that situation. So that's why we thought, okay, let's use the ion itself. So here, that's the typical autocorrelator setup. We thought, okay, let's replace this green non-linear crystal with the atom, with the ion itself, where we want to send the light. Let's get a response from the ion itself. And then we come with the idea, okay, let's use the atomic coherence and somehow read out that thing with atomic coherence. So if you especially overlap the pulse onto the ion and then de-overlap, and then and try to read that response from atomic coherence, how the contrast changes through Ramsey interferometry. So yeah, and this somehow gave us the idea, somehow gave us the answer. And that was matching very well with the applied chipping, applied group linear dispersion that we added to the pulses to the complex chip then. So that's why I wanted to explain this whole thing, because it will take really long, because there's a lot of things there. But this is a black box,
Yes.
and that black box is doing this. And yeah, so especially when you can also search, for example, just for your interest, I want to characterize the short pulse, which is the peak power of few microwatts. I can use autocorrelator, I can use frog, I can use X frog, I can use spider, I can use mud tadpole, I can use blah blah. Which will kind of work? Or you can use street camera, for example. You can say, oh, it's a picosecond, why don't you use a street camera? But still they're limited.
No, then you are using a 200 picosecond pulse and you are taking some of
No. That's the pulse period.
Okay.
Not the pulse width.
Pulse duration, like
If it was 200 picosecond, you could have used very fast oscilloscope.
yeah, no, pulse duration a few picoseconds. So you are taking around 1,000 pulses, for example, because you are generating and you are taking one of this like small number of pulses.
No.
Why not you use femtosecond pulses so you can take much more in numbers?
Good question. Yeah, good question. I mean, but the problem is, my friend, we can engineering this whole system with the femtosecond pulse is way easier. Because okay, maybe I can slightly explain. So because we wanted to produce a lot of power, that was the whole idea. If you read that paper title says multi-gigahertz and multi-watt ultraviolet lasers for this. But now I'm totally saying against what this paper is saying, the first one. Because the reason is that in that sense is perfectly fine. The setup itself is producing, but we need only single pulse. And we wanted to talk with this transition, this guy here, this 393. Okay, and this transition means, okay, now just think. If you have a femtosecond pulse, what would you expect? Do you expect it has a bigger bandwidth or the less bandwidth?
No, I'm just
Just let's little bit argue. For a femtosecond pulse, you will have wider bandwidth, right? It's a very tiny pulse, right? When a picosecond pulse, you have a less bandwidth. Now, if you have a very wider bandwidth, which means, and I told you, is the calcium ion is not just a 3-level atom. What you're seeing here is just the valence electron system, outermost. There are so many levels there. We're going to start talking and smacking on other levels. Okay, so that was the challenge here. You want to have high power with a less bandwidth. And the nonlinear process is power hungry. If you have an energetic pulse, you can produce more power there. I don't want to explain the whole system here.
Any particular reason why you're using calcium ions in?
Not really. We can also use the terbium ion. We can also use barium ions. Yeah. But in this setup, since we had calcium ions, we have control over them, and that was the reason. And one of the reasons that was really, I think, helpful, because we want to smack the ion, because we wanted to drive basically, create a driven quantum harmonic oscillator in the phase space. That eventually creates those entangled state and all those things. And to drive those things, essentially, we need to impart forces. And when you have a lighter ion, then we create large force. But the terbium has 171, the mass number, atomic mass. This is only 40. So that was one of the reasons.
And these ions are in a linear trap, or?
Yeah, in Paul trap. Yeah. Yeah, please, this is a good question. Yeah. Yeah, why can't we use femtosecond pulses? Exactly, but we'll talk about the levels.
But if you use like it is a 7 nanosecond band, like lifetime. If I use 1 nanosecond, it has more narrow bandwidth. So will it work?
We don't have 1 nanosecond level. That I'm not aware of this.
Yeah, maybe 1, 2, 3. I'm also don't know, but I'm just saying,
Yeah.
if I use 1 nanosecond, maybe it work in much better way.
There's not a big difference. It's still same order of a magnitude. If you say like some milliseconds, then it becomes even tougher. Because when you're decreasing the lifetime, then your transitions become very weak. But this is a dipole transition, and that one is the qubit transition. And look at the lifetime there, it's 1 second, 1.2 second. It's a quadrupole transition. It's a very weak transition. And to drive this transition, you need the line width of the laser roughly on order of 1 hertz. Just think about the coherence length of those lasers. It can really go to the moon and come back. It's hundreds of terahertz laser, and the fractional frequency uncertainty is 1 hertz. Yeah?
Yeah.
So just think on the coherence length. So, but the problem with this pulse lasers was exactly, it's another thing. When you have very short pulses, they're very tiny, the coherence length. You need high coherent lasers, and this is difficulty in this experiment. You want to drive a coherent process with a less coherent source. And that's all what we have. That's the fast thing you have, at least in optical domain. Thank you.
That's a major challenge in quantum mechanics. You want to drive coherent processes with partially coherent, beams.
Yes, this is always the case, and building those high coherent lasers, and it's always challenging. It's always challenging, especially this kind of the qubit drives and the clock drives and all these things. And this is I would say the major spectroscopy challenge in cold atoms or trapped ions or clock business. So you need this high coherent sources, high coherence length sources, really high coherence length. For example, in terbium, there's one of the transition that is octopole transition, and that is, if I'm not wrong, it's tens of seconds. I don't know how long. And in our nuclear clock project, the transition we want to drive, that is that has a lifetime of 2,000 seconds. So it's 2,000 seconds, and it has the width of sub-millihertz. Yeah. And it's in the vacuum ultraviolet range. Another difficulty, you can't really propagate those lasers on the free space. They always have to be under vacuum. You have to generate under vacuum, propagate under vacuum, and then you try to hunt for the nuclear transition. It's really, So of course, this is always a challenge.
So maybe one last question. Since you're an experimentalist, how do you compare the prospects of a quantum computer based on ion traps and let's say superconducting qubits?
Yes. Since I work with ion-based companies, so I don't want to be biasness, but I think
Maybe we want to stop the recording.
That's a very good suggestion. Otherwise, they will sue me. But I will say, I think to me, I think this my personal feeling or my personal thought, even when I was not working with them or whatever. So this from the day one, I think ion is a very good candidate because whatever I'm telling you, this laser and that laser and that level is made by Allah. It's all natural. As long as it is calcium forward, it's always the same. The problem with us, okay, we're not integrating nicely, but those superconducting and those things, we are fabricating them. So I have this one major, and by the way, this qubit thing, especially the optical qubit, they're always a clock. It behaves as a clock as well, the same transition. So it's a reference. So we are playing with the references. So what else do we need to build a computer? Of course, we have some engineering challenges on the RF frequencies and those specific materials that can withstand the high voltage and blah blah blah. But on the very basic picture of the qubit or the fundamental side, fundamentally speaking, I think this is the very best candidate. Okay. Because before the invention of quantum computing, what we had? Only clocks. The people were talking, the Dave Weinland group and all these people, they were studying all these things for clocks, nothing else. Especially when Peter Zoller and actually Schlag, they proposed the idea in 1995 on ion trap-based quantum computing. So they were not really sure how to use these motional states and making logic gates and this kind of thing. But when they proposed this thing, after 4 or 5 months, this NIST group performed the first quantum logic experiment based on their knowledge of this clock spectroscopy.
Good, thank you.
Any other questions? All right, let's thank the speaker one more time. Thank you, everybody. I hope we have some tea.
Thanks. Yeah.